When you think about steering an airplane, it seems pretty simple, right? A pilot moves the controls, and the plane just goes where they want it to. But let me tell you, underneath that simple action is a whole world of incredible engineering, solving problems you wouldn't even believe exist.
I mean, really, let's ask the question, how hard can it be? We've been flying for over a century. Surely we've got the whole steering thing figured out by now. Well, here's the twist. It turns out it's not just hard, it's dangerously hard. As planes started getting faster and faster, engineers ran into this terrifying problem. Using a simple control surface at high speed could create forces so powerful, they could literally bend or twist a wing clean off the plane. The very thing you're using to control the aircraft could actually destroy it.
And that brings us right to the heart of the matter, what we could call the speed barrier problem. It's this fundamental battle between what the pilot wants to do and what the laws of physics will actually allow at incredible speeds.
You see, aeronautical engineers found themselves in this classic Goldilocks situation. At low speeds, say when you're coming in for a landing, the controls feel mushy, weak, and sluggish. But at high speeds, those exact same controls become super effective, almost too effective to the point of being dangerous. So the big challenge was, how do you design a system that feels just right no matter how fast you're going?
And it gets even weirder. There's this bizarre and frankly terrifying thing called control reversal. Imagine this, you're flying slow and you want to lift a wing. So you move the aileron. But instead of lifting the wing, the control surface creates so much drag that it actually causes the wing to stall and drop. Your input does the exact opposite of what you intended. Talk about a nightmare scenario. So, how in the world do you solve all these conflicting problems? Well, you can't just use one tool for the job. Instead, engineers had to get creative and develop a whole toolkit of different control surfaces, each with a very specific purpose. First up, we have the spoiler. This is a brilliant solution for high-speed flight. Instead of using an aileron that could twist the wing, a spoiler just pops up from the top surface. It does exactly what it sounds like. It spoils the lift on that wing, causing it to drop, and the plane rolls, all done safely without putting a dangerous strain on the wing structure. And then things get even more clever with these hybrid surfaces. Take the flaperon. It's one control surface that does two jobs. If you move them both down together, they act as flaps, giving you more lift for takeoff and landing. But if you move them in opposite directions, they act as ailerons to roll the plane. Super efficient, right? You see these on jets like the F-16. Now, on a beautiful delta-wing aircraft like the iconic Concorde, you'll find something called elevons. These combine the job of an elevator, pitching the nose up and down, and an aileron for roll, all into one elegant surface on the trailing edge of that massive wing. And here's another really smart one, the taileron, which you'd find on a jet like the Tornado. Instead of using the wings to roll the plane, the entire horizontal tail moves. Move them together and you control the pitch. Move them in opposite directions and you roll the plane. The genius part is that this takes all that twisting stress away from the wings. Okay, so we've got this amazing toolkit, right? Spoilers, flaperons, elevons, tailerons, ailerons. But this creates a totally new problem. How is one human pilot supposed to manage all of that at once? How do they decide in a split second whether to use the spoiler or the aileron or the taileron? It's too much. It's information overload. The solution wasn't a bigger instruction manual. The solution was a complete technological revolution. And this is where our story shifts, from the physical surfaces on the wings to the systems that control them. We're talking about the evolution from human muscle power to silicon microchips. And this evolution really happened in 4 big steps. First, you had purely mechanical systems, literally just wires and pulleys connecting the pilot to the controls. Then came servo-assisted, which is basically power steering for a plane, using hydraulics to help the pilot out. But the real game changer was fly-by-wire, where all those heavy mechanical links were replaced by simple electrical signals. And today, we even have fly-by-light using fiber optics that are totally immune to electronic interference. But here's a weird side effect of all this progress. Once you take away that direct mechanical connection, the pilot loses something crucial, the natural feel of the air pushing against the wings. They can't physically sense the stress that's building up on the aircraft as they maneuver. So what do the engineers do? They had to literally invent that feeling and put it back in. They developed these amazing systems for artificial feel.
A really clever device called a Q-feel unit constantly measures the air pressure, and as the plane goes faster, it automatically makes the control stick stiffer and heavier, perfectly mimicking the natural forces a pilot would expect to feel. And this, right here, is where everything comes together. Fly-by-wire wasn't just about making things lighter. The crucial point is that it put a computer in between the pilot and the airplane. And that computer could finally solve that information overload problem. It can manage that whole toolkit of control surfaces automatically, making thousands of decisions every single second.
And this level of automation didn't just make flying a little easier or a little safer. It unlocked performance and maneuvers that were, before this, completely impossible. So, what does a fly-by-wire system actually get you? Well, it dramatically improves performance and fuel efficiency. The computer can coordinate tiny movements across all the control surfaces that are way too complex for a human to even attempt. This allows a plane to fly much more safely near its limits, and you can even program the software to make a small, twitchy fighter jet handle like a big, stable airliner, or vice versa. A fantastic example of this is something called direct lift control. Normally, if you want to climb, you have to pull back and point the nose of the plane up. But with DLC, the computer can instantly coordinate the flaps and elevators in perfect sync to make the entire plane just jump upwards, without its nose ever pitching up. It's an almost magical, instantaneous burst of lift. And this isn't just theory. The source material points to the famous Harrier jet, which uses its unique engine to do something similar, to jump suddenly upwards or downwards. This wild maneuver turned out to be incredibly useful for, dodging missiles in combat, a real-life application of advanced flight control. Now, of course, I know what you're thinking. If we're relying this much on computers and hydraulics, what happens if something fails? Well, the answer is redundancy, a whole lot of it. A big plane like a Boeing 747 doesn't just have one hydraulic system for its controls, it has four completely separate, independent systems, just to make sure there's always a backup, and a backup for the backup. When you put all these pieces together, you start to see the bigger picture. This isn't just about a change in technology. What's really happened is the creation of a brand new partnership between the pilot and the aircraft. And this table sums it up perfectly. In the old mechanical systems, the pilot was an operator. Their job was to figure out how to physically move the surfaces to get the plane to do something. But in a modern fly-by-wire system, the pilot is more like a system manager. They just tell the computer what they want. I want to climb, or I want to turn left. And the computer flawlessly figures out the how. It's a fundamental shift. And this incredible journey from simple pulleys and wires all the way to intelligent automated systems leaves us with one last big question. As aircraft keep getting smarter, more capable, more autonomous, what does that mean for the future role of the pilot in the cockpit? That's really the next chapter in this hidden genius world of aircraft control.